Okay, that's good afternoon. Can you hear my voice clear?
Clear, sir.
Yeah, okay. Okay, we proceed with chapter 2. So, before we start, I've seen that some of you haven't submit the quiz that you learned. So remember, quiz is 5%. It's quite big, 5%. So if you don't submit the quiz, you will lose the 5%. Okay, because sometimes it helps to increase your mark, particularly if your mark letter will be in the borderline. So I can just increase based on the quiz. If you just submit and do all the question, doesn't matter is it correct or no, still give you mark then. Okay. Okay, chapter 2 is single phase. If you are still remember our lab 2 last time, lab 2 you connect. There are in the one in the below there, the power source. You have L1, L2, L3, and neutral N, right? So you connect only L1 and neutral, L1 and N. So that one is single phase. If you connect L1, L2, and 3 and neutral, all of them, that one is 3 phase. Okay. So single phase usually used in residence at homes. The 3 phase usually used in industries. Okay. There are advantage and disadvantage of each phase. So we'll discuss later. So introduction, second SC in resistive circuit. Resistive circuit, alternating current and resistors. Your lab 1. Yeah, lab 1 only consists of resistor. Okay, that one we call it resistive circuit. And then SC in inductive circuit. So if you combine resistor and inductor, we call it inductive circuit L. Okay. Then capacitive, when you add capacitor, call it capacitive circuit. And the connection could be series or parallel. Okay. So I assume you have seen the video I upload at YouLearn and do the quiz. So some of you ask question, which is good. That means you go through the slide and did the question. So if you have any problem, just ask me. I will always I'll try to respond. Maybe it's not a fast response, but I will respond because I have also something else to do. So, but I will respond. Just ask me. Okay, some of you asked about this question here. Example. Let's see. What's the question? Okay, listen. Consider a purely inductive circuit. L, R and L, voltage across 0.2 Henry, inductive is VL, 100 sine 400T plus 70 degree. Determine IL and sketch its phasor diagram and waveform. Okay, VL is given, L is given, so you have to find the IL and sketch the phasors and waveform. Okay. One of you asked about this one. Where can I write? Okay. Okay, this one. How do you get in phasors? Look at the phasors here. How do you get 7.7 and 0.884? That's the question. Because you can't find any the number here in the questions. Okay. Okay, look this one. If you look this one. Okay. The given one is PL here. 100 sine for 100T plus 70 degree. So 100 there is the V maximum, right? V maximum. Just like a normal sine wave. Right? Omega T. So this one is always the maximum. Maximum. Okay. So 100 is maximum, but for phasor form, VL, V, and then the degree there. How many degree? This one. Phi here is always the RMS value. Root mean square or average. So the relation between Vmax and VRMS is our class last 2 weeks equal to Vmax divided by square 2. So you get the 70.7 is from 100 divided by 2, right? So that one is this one. And then I current 0.884, the same. So that one is average. So you find the I maximum, which is this one. I maximum, right? So that one come from 1.25 divided by square 2. So this one is 0.884. Okay. Just interrupt if you have any question, or you can type in the chat room. Okay, then since you have seen the video, I will just go to the conclusion. Okay, here. Pure resistive means V and I in phase, mean they have the same phase, no phase different. Okay, so the wave of V and I, the same phase means they start at the same point and they end at the same point. Look, there's the example here. Resistive. Okay, this one. Purely resistive. They start at the same point. Yeah. They end at the same dot here. That means in phase, no phase different. Although they have different amplitude, doesn't matter. But look, you only look at the phase. Okay. That's what I mean by in phase. And then pure inductive. V leads I by 90 degree or I lags V by 90 degree. If you look at the pictures here, where's VL? So this one, oh, this is this one. Oh, no, not this one. Okay, this one. This one. So view F lead by 90 degree. F start first. Lead means start. Is here. We start first. Start at different point, right? Start at different point. This one is 90 degree different. This one and this one, 90 degree different. Okay, 90 degree is pi over 2. This is how you draw the phases. If you look at the difference, it's 90 degree between V and L. V is lead by 90 degree. Okay. Okay. That is inductive. Capacitive is the other way. I leads V by 90 degree, V lags I by 90 degree. Okay, some of you are difficult to memorize this, so use this simple civil here to replace this, because some of you are having difficulties to memorize this, so just use this one. This one is the addition on it. Oh, basically, pure resistive is no phase different. So this civil is applied for inductive and capacitive. So how? C means capacitive. Capacitor, capacitive, C. Okay. So since I, after C is I, that means I lead. Next one is V. So I leads V for capacitive. Okay. Next one, the blue circle here. The blue circle, V. First V leads I. Then I lead, V leads I for L. L means inductive circuit. So that's how you memorize. Civil, capacitive, C is capacitive, I current, lead voltage. And then VIL, voltage, lead current in inductive. Degree is always 90 degree. Okay, that's how you the other technique to simple one to memorize to understand the pure inductive or pure capacitive. Okay, yeah. This one, you have done this, and it's not difficult how you connect in series and parallel. So just skip this one. Let me go to okay here. Just to give you some insight. Why is it minus here? Well, let me go through this one first. This is parallel. Can just go through this one. 1 over Z. Okay, this one. One over Z for RSC in parallel. Okay, because parallel. So 1 over Z. So some textbooks 1 over Z equal to Y. 1 over R equal to G. So the reactive, this one, equal to B. Y is admittance. Z is impedance. Impedance. Y is admittance. The unit is impedance. The unit is ohm, right? Ohm. Admittance. The unit is Siemens. Because sometimes it will be easier to use Y instead of Z for calculation purpose. Okay. Okay, let's see next one. Okay, solution for essay series parallel can be done by method phrases and complex number method. Okay. This is phrases. Okay, let's compare. The given parameter. Okay, this is the circuit. 100 volt. You have RLL in parallel. Okay, frequency given, R given, L given, C given. You have to find current in each branch. So IR, IL, IC, and I total. Okay, IR is V over R. Okay, 2 IR. Okay, IL V over XL. Okay. Okay, why is it minus here? Let's see. This one minus, right? Because in inductive, remember this formula here, inductive. Inductive is the blue one. V leads I by 90 degree in inductive. V leads I. If you turn it the other way around, that means I lags V. I lags V by 90 degree. Okay, lags means minus. Okay, so it's minus then. What about C? C here positive, this one. Why? This is for capacitive. Look at this one, the red circle here. Capacitive, I leads V by 90 degrees. So I leads V, leads mean positive then. So it's positive. This one for phasors, if you compare to complex number method, okay, the formula is all the same here. Okay. For branch, for R, since only R, so there is no reactance, so this is 0, right? For L, since only L, so R is 0. So how do you get this one, XL? XL equal to omega L, right? Or 2 pi FL. F is given, 50, L is given, so you can directly get the answers. Okay. So this is 2.12 is from 100 divided by 47, sorry. Why is it minus 90? Because in phasors, this means if this is division, that means you have to subtract. That means 0 degree minus 90 degree equal to minus 90 degree. Okay. For C, this is minus this one. For C, XC equal to XC equal to 1 over J omega C. Right? Or J 2 pi FC. Right? If you take J up, can I write in here? J going up 2 pi FC, J will be minus then. Because it's going up. So you have this minuses come from there. Okay. So since this is minus, so this one is minus. So 0 minus minus 90. 0 minus minus 90 will be plus. Complex number method. Okay, yeah. Okay, this is just to show you the effect of frequency. This is just now the formula for reactance of the inductor. So since XL has linear relationship with F and with L, so if we increase F, this one will also increase reactance of the inductor. Okay, if you increase L, inductance, XL will also increase. Okay, this is what the formula explain. Frequency double, reactance double. F double, XL double. F half, XL half. L double, XL double. L half, XL half. Okay, linear relationship. Okay, the opposite of that is the capacitor. The opposite. So Xc has inverse relationship with F and C as well. Inverse relationship. So if you increase F, Xc will be decreased. If you decrease C, Xc will be increased. So it's the opposite. Okay. What happens if you put F equal to 0? 1 over 0, infinite. Infinity, yeah? Infinite. So if C is doubled means 2. So 1 over 2. 1 over 2 is half. So Xc will be half. Okay. Okay. Next, skip this one. Oh, this is power. Okay, power, there are some terms you have to understand. In DC equation, this is, I think most of you are familiar with this one. P equal to VI. Okay, so in AC, power equal to real power or active power. Okay, so reactive, there are also non-reactive power. Reactive power. Energy that was delivered to the load and then it is returned to the source and so on. So go back and forth between the load and the energy because of these two components L and C, inductor and capacitor. Okay, so the active power for inductor is QL, the active power for capacitor is QC. Okay, so the formula, okay, this is for pure resistor only. This is the formula, resistor only. So basically start from V times I, right? This is RMS, correct? This one. So if you want to put V max, VRMS equal to V max over square 2, right? And then I RMS equal to I max over square 2, right? So equal to V max times I max over 2. This is where the formula comes from. Okay. The one is for pure resistive and then for inductive. Okay, inductive is reactive power QL. This is the formula. This one. So basically, just it's similar VI or I times R for resistive. But for inductive, that means times XL, right? Times XL. Or you can also do this because, let me write this one, sorry. VI, VI equal to V squared time divided by R. So you just replace the R with XL. If you replace R with XL, this one will be L over XL, right? Okay. The same applied for capacitive. Okay, this one. Capacitive. exactly the same. It refers only in the formula or the of the XC and XL. Okay, we have power, reactive power, average power, and then we have apparent power. Apparent power S is power being supplied to the load. Active power, real power is the power from the source. Average power is basically maximum power divided by square 2. Reactive power due to the inductor and capacitor. And then apparent power that is supplied to the load, withdrawn by the load. Okay, VI, formula is VI, same. Okay, this is a relation between PQS. P is average power, Q is reactive power, S is apparent power. Okay. P resistive, so X0 CZ equal to R, V times R, S equal to P, Q equal to 0 because there is no inductor and capacitor, and so on. Generate this one. I want to go to, okay, power factor. Power factor, let me go to this way. If you see the angle there, there's an angle there. This one. So basically, power factor is equal to cos of the angle, different angle between voltage and current. Okay. Can be categorized into unity, lagging, or leading. Unity means I and V has no degree, same degree, in phase, no phase different. I and V, or pure resistive. Lagging, this is what it means by lagging. If I lagging V, the PF is lagging. If I leading V, PF is leading. Okay, what about this one? This one, I lagging V because V above. V here is above I. So V leading I or I lagging V. So PF is lagging by 0.87. 0.87 is from cos 31.8 equal to 0.87. 85. This is important because to measure the usage of your electricity bill, power factor. Okay. Okay, next. Okay, we'll skip this one. Okay, measurement. Multimeter. This is your multimeter. I'm sure you familiar with this one before? How do you measure as voltmeter? How do you measure as ammeter? Okay. So in series, which one in series? Series is ammeter, parallel is voltmeter. Okay, this is connection parallel. Okay, this one. For current, okay, sorry. Because multimeter can act both as ammeter and voltmeter, right? So, okay. So current measurement in series, voltage measurement in parallel. Okay, average power given by wattmeter. This one. Cos of the V and I, the difference between degree of the V and I. Just now, V, I, this one. Okay. Okay. Okay, example for circuit the following figure. What does the wattmeter indicate? If A, V load 100, 0 degree, I load 15, 60 degree. What is the watt in here? In where? Let me write. Okay, this is the wattmeter. This is the load. This one will measure this one. We'll measure the one in here, right side. Okay, what will be the watt then? Remember the formula just now? Okay. V equal to VI cos V cos, right. Right, so V is 100, I is 15, V 0, is it 0? Yeah, 0, 0, 0, I 60. Cos minus 60 equal to cos 60 equal to 0.5, half, right? So times 15 times 0.5, this one, 750 watt. Okay, also B the same. BV is 100, I is 15, so cos 10 minus 30, cos minus 20 then. Okay. That one is for wattmeter. Okay, it should be noted that wattmeter reads only for circuit element on the load side of the meter. Load side. In addition, if the load consists of several elements, it reads the total power. Okay, this is the, if you look circuit here, this is the wattmeter. The load side is this one, the green one here, the load side. right beside the after the wattmeter. So they will read, the wattmeter will read the load side beside the wattmeter. Because we also have another load here near the source, this one and this one. But since they measure in here, wattmeter, so they will only read total of this one only. So 700 watt plus 40 plus 10 equal to 750 watt. Okay, if you put the wattmeter in here, for example, in here, the wattmeter, so what will be the total, the reading of the wattmeter? So this one is 750, right? So plus 300 plus 100, right? 1150 watt. Okay, then we have resonance in IC circuit. This one very useful in communication. Okay, resonance. What condition? Okay. Okay, this one where VD and IT of circuit are in phase. Okay, look at this keyword here. The keyword. This is the keyword. Are in phase. That means pure resistive. Pure R. Okay, pure R. No XL or no XC. Okay. Okay, this is example. So Z in here, impedance equal to R plus XC minus XC plus XL minus XC. You know, I told you why XC is a minus. Okay, so because we want to get pure R, that means this part. Okay, let me write this part here must be equal to 0. So the Z will be only equal to R. This one. So this one must be 0. And that means XL equal to XC. Right? XL equal to XC, then this one. C omega L, this is the formula. And then omega goes here. You have this one and you have this one. Omega equal to 2 pi F. So F equal to this one. This is, they call it resonance frequency. Frequency where the circuit is a pure resistive. Okay. Pure resistive. Okay. This one you can just, this is dissipation, this is This is, we discussed this one. Oh, this one, the new one is a Q factor. There's a Q factor here. Reactive power, average power. Reactive power is this one. Due to the inductor. Average is resistive only. Okay. So if you delete the I, so XL, the I, so it will be this one. If you want to, this one. Okay. Quality factor for resonance frequency. And then I can just try this one. This is why they call it resonance, right? So you can find C here. Okay, and this is quality factor. Okay. Okay, this is in parallel. Just now is in series. Just now in series, where x L equal to xc, right? So equal to 1 equal to c. So omega equal to LC. So F equal to 2 pi LC. This one for series, but for parallel, it's different case. So this is how they got for I inductor for resonance circuit. Resonance circuit means XL equal to XC. You can take a look at the textbook later for the detailed explanation of this slide. It's all there. Okay, this one, skip this one series. Give resonance, the keyword here, give resonance. Okay. Remember the first series, this is the formula. So you find C. F is given, L given, so you find C. Okay. So, okay, that's it for today. Okay. Also, some of you asked about there are wrong answers for one of the questions. Page 33 or something. Is it 33? Yeah, this one. Example 2. So resistor connect in parallel with pure inductance. Resistor, pure inductance. Okay. This one is 110, 2K, 50 ohm. This one is 3 millihenry. The branch circuit and supply current. The branch current. You have to find IR, IL, and supply current, I total. Okay. So IR, look here, because it's parallel, so the voltage will be equal in everywhere. So IR equal to V times R. V is 110, R is 50, right? So 50. Is it? Yeah. So this one is 2.5. Okay. Two point four.
2.2 lah, sir.
2.2. Right, 2.2. So it's 2.2, huh? 2.2 ampere. Okay, so the answer is different then. It's not the same. That's why I asked you to prove, right? My question is prove the answers. So there can be two options. There can be only two options there whether the answers is correct or wrong. Okay, so if the IR is different, that means the one that will affect is the circuit phase angle and circuit impedance. As for IL, there will be no affected by R, right? Because IL equal to V XL. V is 100, XL2 by F is 2K. L is 3 milli. So this one, okay, so 110 over 4 pi. 4 pi, right? 110 over 4 pi. Okay, so that will be for IL. 2.2 correct. So 2.2. Okay, that will be all for chapter 2. So go through again slide. If still have problem, have question, ask me. Can ask me directly, no problem. I will try to answer. Some of you did, which is good. So you can also discuss with the friend. If you are stuck, ask me then. Okay, if you have no questions, I'll see you next week during the lab session. We'll have lab 3 next week, like usual. So lab 3, I have uploaded the lab sheet. You can bring along the lab sheet. And yeah, just like normal lab. Okay guys, I'll see you next week during the lab. Good day.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.